to steel. Okay. How did we choose? You can choose brass. Okay. Later on, we will choose brass. Okay. Okay. Equivalent to steel. Okay. So does that make sense? Okay. Now this is where your knowledge will come in. Okay. So let's say if the geometry of brass is that wide, okay, it is 5 square wide. Yes or no? If you change the middle material to become steel, for our ease of calculation, will it be wider or will it be narrower? Anyone, please. Do you need a wider piece of steel or a narrow piece of steel if the strength is to be maintained? Anyone? Anyone?
Narrow.
Yeah, narrower. Kelvin, wider. Right? Narrower, right? Right? So the strength as in the Young's modulus, Louis, okay? Not yield stress, okay? Right? So why not use stress? Because in our concept that we learn, we will not stress the material to its yield point. We want to avoid that. Okay, so the strength is in terms of Young's modulus. Okay, you can see that, right? So we make it narrower. So the strength, okay, the ability to withstand the structure strength is the same. Okay, because we narrow it down. Okay, so brass you have to have thicker, steel you have to narrow it down because the Young's modulus is twice, right? So what the okay, let me now do another case. Yes, someone has a question. Yes. Okay, no question. So if let's say now we change, okay, the reference material. So let's say now I have case number 2. Okay, I'm going to draw case number 2 down here. Case number 2, right? The reference material, okay, the reference material now is what? Is brass. Okay, this for bending about the, okay, Curtis, later on when I change the axis or when I reorientate, I'll show you what happened. Okay. So
Sir,
yes,
um, so that drawing you just did, with the steel and the change sides of brass, was that in terms of like the Young's modulus then? Like,
yes,
okay,
it's just purely Young's modulus. Okay.
okay,
Okay. Why that is because this formula where you have stress y or moment over second moment of area multiply a certain distance is actually suitable for one material only. Okay. Now we have two material. We want to force it to obey the rules of stress x is equal to mz over my over iyy multiplied by z. Okay. We want to force it. The only way to force it in is we have to somehow put in a coefficient to to make it equivalent to just one material. Okay. So now what if our reference material is brass? Okay. What if our reference? So now we know that N of steel will be equal to E of steel divided by E of brass. So now this is 200. This is 100. So it's as good as equal to 2. And then the next one is the N of brass. So it's equal to E of brass divided by Young's modulus of brass. And then this is equal to 1. Okay. So now what happens now is now the whole structure is made of what? Is made of brass now. Okay, so now the whole structure is made of brass. So the center part, remember the center part, we have how many squares? We had 5 squares. Okay, so we have 5 squares. 2, 4, 5. I should make it even number, it's easier to draw. Okay, so this is 5. So this is now brass. So for this case, brass is the equivalent material. Yes, or the reference material. Now, can anyone tell me if the top and bottom layer we change to brass, will the top and bottom layer be wider or narrower? Anyone, please? Anyone?
Wider.
Yeah, wider. Right? So it'll be like, yeah, so it'll be like this with white. Then the strength will be equivalent. Okay. Right? So this is, now we change all to brass. Okay. Can someone comment on what you see? Please, can someone comment, please? Can someone make a comment on what you... Yes.
So is this supposed to show the like equivalent geometry change you would need to make then? Like, is that
Yeah.
what this? Okay.
Yep. But what is the interesting feature now? Anyone? What can you see that, what is always constant with this tree diagram, okay? From the original case 1 and case 2, what is always been held constant? Anyone, please?
Tree is wider than brass.
Huh?
The geometry of tree.
Wait, someone got it right. Kevin Wang, you are right, okay? The height did not change, right? And Jenna, you also get it right. The height did not change, okay? It's a very interesting, it's a very interesting observation that you guys make now, right? The height did not change deliberately, okay? So the height, okay, what you see over here, the height is held constant. You have to get this concept right, okay? The height has been held what? Has been held constant, okay? Any idea? Why? Why the width can change, but you cannot change the height? What is happening down here? Anyone, please? What is happening? Why do we only change our width? We dare not move our height. Okay, why is that? Yes.
Because it's sandwiched.
Hmm?
Because it's sandwiched.
Yeah, but sandwich, I can also make it thicker, right? Rather than using a thin sliced bread, I can use a Texas size loaf, right, which is twice the thickness. But we did not do that. Okay, we kept the thickness the same, but we only changed the width, right? So I'll give you guys a hint. Okay, this is because of second moment of area. What do I mean is to simplify. Okay, simplify to calculate the second moment of area. Now, what do I mean by that? Okay, if you look at the calculation of the second moment of area, right? So we still need to calculate second moment of area, by the way. We still need to calculate, yes? Okay, so the original formula is, you guys know by now, is width times depth, right? Cube divided by 12, right? Plus by width times depth, right? Big Y minus small y bar, or big bar squared, right? Now, with a sandwich material, so this is for a single material. Right? So if you're going to change to a sandwich material, see what I'm doing with the n coefficient, okay? N W multiplied by D cube divided by 12 plus by N W, okay? Now, N W are two separate terms, yeah? I deliberately put them in brackets to show you the N is changing the what? The width. This is for sandwich material. Can you see what is going on now? Yes or no? Right? It is to ease our calculation. Okay. So when I put a coefficient like this now, okay, when I put a coefficient, means the coefficient is only changing the what? The W. Okay. The coefficient is only changing the what? The W, the width. Okay. If we also change the depth, or let's say now, okay, let's say now, okay, I don't care. I want to change the depth. Okay, I want to change the depth. So for all this configuration, okay, for all this configuration, okay, so the moment, right, the moment is applied this way. So I'm going to draw the moment vector. Okay, so this is moment about y-axis for all of them. Okay, right, that is our moment about y-axis for all this. Okay, I know someone asked, what if now moment is about z? I will do that later on. Okay, now for this case, right, if let's say we decide to change our height, okay, so let's say we decide to change, you realize what, let's say now you want to keep your width constant. Okay, now the problem is this term down here and all these down here, they will have issue. So now I'm not saying that this is right. If let's say now we change, right, we change depth, right, now we change depth. Okay, we did not, so this will be equal to I is equal to W and D cube divided by 12 plus by width and multiply by D, and then it will complicate, right? Then you have to change N Y bar something like that squared. Okay, I'm not saying that this is the right equation, but it makes it more complicated. Yes or no? First of all, this is a coefficient. You don't cube a coefficient at all. You cube a coefficient, what does it mean? Means if we use brass as a reference material, this coefficient means the steel, okay, the steel or the brass equivalent to steel is n to the power 3, right? Coefficient has to be left alone, not to be multiplied or change of units. Does that make sense to you all now? Okay, is to use the analysis. Okay, okay. Does this apply for bending moment and shear or just bending moment? Mina, I'm going to focus on bending moment and axial loading. Shear VQ over IT. No, shear. This don't apply. I've not talked about shear yet. Okay, Mina, I'll come back to you in an answer regarding shear. I don't want to blare something up until I prove it mathematically. Okay, I don't just blare. Okay. Okay, so this is the reason why. Okay, this is the reason why depth is held constant. Okay, that is why we hold the depth constant. Now, someone asked, okay, Eugene, okay, this is, I'm happy. This is very, very good. Now, what if, okay, now what if now the moment is in the y direction? Okay, so if I were to draw our transformation, sorry, I did not draw that. Right, so when this is the case, right, moment about y, so we know that this will be our, so if we are taking our moment, this will be our width. Okay, this will be our, no, what am I talking about? Hold on, today I'm having something not working in my mind. I do apologize. Okay, so m stress x is equal to mz over izz multiplied by y. Okay, so for this case is, so